So why the same copper wire, you make it like a spring and you send a varying current, then we'll get induced current. So shall I say that the dimensions of coil matters here a lot, the shape of the coil, not like a the area of cross section of wire, the shape of the coil. So therefore now this particular circuit, this particular instrument, I'll give a good name, solenoid, or I'll call that as an inductor, induced current, no, inductor, which will induce current, that one. I'll call that as inductor. So what is the property is acquired? It has acquired now a property to oppose varying current. So the measure of opposition by this instrument or by this device to the varying current is called like a inductance or self-inductance of a coil. I'll bring a quantity called as inductance. I'll define like this. The measure of opposition to the varying current is defined as the measure of opposition to the varying current by a coil. This is called like a inductance, or you can give it as name self-inductance. So where is that current is flowing? The current is flowing, where the current is flowing? The current is flowing in the coil. Where the varying current is flowing in the coil. Where that induced current is produced in the coil. Who will produce that induced current? The coil. High is the external current. See, I'll connect one cell and that cell will push this external current. High induced is produced by the coil. I think you should have a clarity. So what about I induced? This is produced by a coil. What about I? I is what? Supplied by the external source. So the measure of opposition to the varying current by a coil is called as self-inductance. If current increases, the coil will try to decrease. If current decreases, the coil will try to increase by pushing current in the direction. You look at I induced in the direction of actual current. I induced opposite. Why the polarity? This will behave like a cell, no? This will behave like a source of EMF, which will generate a I induced. So in what direction I induced? Towards left. So this terminal, left terminal should be positive. All of you look at here. It is trying to oppose the actual current. So therefore, plus this one. This should be positive term, this should be negative term. Look at this one now. Current is decreasing. So what this coil will do, will try to increase that current. So it will push induced current in the direction of actual current. So how I induced is flowing towards right. So therefore, this end should be positive. So the polarity for this inductor depends on actual current or induced current. The induced current, are you able to understand? In both the cases, actual current is flowing from left to right, but induced current changes direction based on how the current is varying. Now the same copper wire, I'll pull it, I'll stretch it so that it will become again a wire, straight wire. I'll send a varying current. I don't get induced current here. So a special property this particular copper wire acquired when it is wound as a coil, when it is wound as a spring. And I'll see that number of turns will be very close. The turns will be very close to each other. Got this? So there's a one basic idea, and whatever that induced current will be very much less than actual current. These are very important, so very troublesome, not mentioned in the book. So practically when I check it, no, see, we can't measure induced current, just only theoretical on paper we can do it. So can we have ammeter which will read high and I induced separately? No. If you connect any ammeter, what it will do? It will read resultant, no? And I can check practically that, so like theoretically I can make a analyze that the induced current will be less than the actual current. So what it is doing, it is actually opposing that one. So the measure of opposition to varying current is called like a self-inductance of a coil. Now this particular thing, so let's come back here. Look at the net flux and current, how they are directly proportional. They're directly proportional. So from here, the flux linking a coil, the flux linking a coil is directly proportional to the current flowing in the coil. So this, to remove this proportionality, I'll bring a constant called as self-inductance. Where is L? The symbol for self-inductance is L. And what is the unit for this? What is the unit? Unit is called as symbol L for self-inductance. And in what is the unit, like Farad for capacitance, ohm for resistance. Similarly, Henry for the self-inductance. So now I'll define self-inductance. What is the self-inductance? Net flux linking the to the current flowing in the coil. So what is the formula for net flux linking the coil? Mu naught n square S I by L. So this will cancel out. So what is the self-inductance of a solenoid? Mu square, mu naught square, n square by L. What is S area of cross section? Can I also write this in another form? S into L by L square. I just said one L. S into L will become volume. N by L is number of. So what is small n? Small n we should call it as number of turns per unit length. And what is V? V is called as volume of solenoid. So what this inductor does now? So I'll call this, and it depends on what you see. L, physical length, V, and you see like an area of cross section, length. So shall I say it just depends on the physical parameter like capacitance F naught A by D. Here also the inductance, it depends upon the physical dimensions of the coils. Self-inductance depends on physical dimensions of coil. So there's one basic idea of the self-inductance. So now let's see that what all it can do. If current is increasing, can I try to oppose it? Yes. If current is decreasing, can I try to oppose it? Yes. Now look at this same inductor now. Is it storing any energy? Yes, it is storing magnetic field energy. It is storing magnetic field energy. So can we calculate how much of energy present in that? B square by 2 mu naught. B square by 2 mu naught energy density, and we know volume, we'll get the total energy. That energy of the coil can I express in terms of self-inductance. So I'll move on to the next concept. Again, what is the resistance? Go back to some very basic things you learned. What is the resistance? Just let me stress once again. What is the resistance? It's a measure of opposition by a conductor to the flow of current. That's all, not to the direction of current, flow of current. Current increasing, decreasing, irrespective of that, conductor will oppose that flow of current. What about inductance? It's a measure of opposition to the varying current, not to the amount of current. It will just oppose varying current. If a constant current flows, no inductance. Means, sir, in the same coil, I'll send a constant current. Will there be induced current? No. We don't get any induced current. In the same, like a coil, solenoid, I'll push a constant current. Let this current I I equal to I naught. Will I get induced current? The answer is no. Able to make it out? So when do that EMF will be generated? When do EMF will be generated? When current through the coil is varying. So therefore, some sort of like a potential difference is set up, or EMF is generated. So let's try to calculate that EMF generated here. So whose help I should take? I'll differentiate this. I'll differentiate that equation. d phi by dt. L di by dt. From Lenz's law, what is d phi by dt? Should be equal to minus C. So another definition for the self-inductance. And look at that EMF induced, it will oppose cause, no? What do negative sign indicates? The negative sign indicates the EMF induced is such that it will oppose the cause. What is the cause? The varying current. Internal resistance will be there. I'll put later on. Let's focus on self-inductance first, because any conductor must have resistance. I'll put later on that one. So now how you define a inductance, self-inductance, which is having 1 Henry. A coil is said to have 1 Henry when an EMF of 1 volt is induced when a current across it varies at a rate 1 ampere per second. So how you define 1 Henry? How you define 1 Henry? When an EMF induced across a coil is 1 volt, when a current varies at a rate of 1 ampere per second. The coil is said to have 1 Henry when it produces an EMF of 1 volt, when a current across it varies at a rate 1 ampere per second, whether current increasing or decreasing, just telling varies at a rate of 1 ampere per second. Like this, we define 1 Henry. Our definitions are very important. You have to be careful. Always we should define for unit variation, not like 2 volt. If an EMF of 2 volt is produced when current across it varies 2 ampere per second, then also you'll get 1 Henry, but it's not a definition. We should always go for the unit variation. Means like unit volt is generated when unit current varies per second. There's a scientific way of defining SI units. Now, so I'm bringing the idea of EMF induced. So therefore, where all numericals are there, can I replace this cell with a, can I replace this coil with a cell S? So when you're replacing this coil with a cell, you should be careful. What is the self-inductance of a coil? It depends on what? Number of turns, area of cross section of that, and the length. So this is something very important formula is what we have generated. The self-inductance of a coil, what happens depends on these things. So this particular shaped structure, I'll give a name called as an inductor. So now we will do naming for this. What is this? This is called like an inductor. So this particular structure is called as an inductor, that one. A solenoid in the magnetism chapter only, we are calling it as now an inductor. Got the idea, no? What is the self-inductance of an inductor? Inductor means it should flash for you. Different shaped coils will come. We don't call them as inductor. A structure, a coiled structure of this shape is called as an inductor. I'm making things clear. The moment inductor comes, the spring idea, the diagram of spring should flash for you. Any energy stored by the inductor according to this? So let's go for the energy equation. E is equal to, so how you define power across the coil? This is a L, this is a current. Let EMF induced be E.